Hello everyone, welcome back. Today we are going to understand and code TurboQuant from scratch in PyTorch, a paper from Google Deepmind that gives provably near optimal algorithm for compressing high dimensional vectors. This is the math that makes it possible to run LLM on your phones, compress KV cache by 5 times without losing the quality, and search billions of vectors in milliseconds. And here is the most beautiful part of this paper. It mathematically proves that no other algorithm in the universe can do better, and also shows that TurboQuant is within the factor of 2.7 of theoretical limit. We will also follow the same pedagogy as before, that is, intuition first and code immediately after. So let's get started. Let's start from absolute basic. Your computer represents a floating point number in 32 bits. That's around 3 kilobyte per vectors. Now imagine you have a vector database with 1 billion embeddings for semantic search. That's around 3 terabyte just to store the vectors. Before any indexing, before any search infrastructure, that doesn't fit in RAM on any single machine. Now imagine you are running an LLM with 100,000 tokens, context window. Each token generates a key vector and a value vector at every layer. If your model has 32 layer and each KV vector is 128 dimensional float 32 value, your KV cache for one sequence will be around 3.3 gigabytes approximately per request. If you want to serve 100 concurrent users, that's 330 GB of KV cache alone. It's completely impractical. Here is what a vector quantization solves. Instead of storing vector in a 32-bit floats, we compress each one to a small integer like 3 bits or 4-bit or even 2-bit. So a 4-bit quantizer cuts memory by 8 times, a 2-bit cuts it by 6 times. But quantization introduces a distortion, which is the compressed vector is not identical to the original. And the question the TurboQuant paper answer is, how much distortion do we have to accept at a given bit budget, and can we get close to that theoretical minimum? The answer turns out to be the theoretical minimum distortion at b bits per coordinate scales as 1 divided by 4 to the power of b. And TurboQuant achieves approx 2.7 divided by 4 to the power of that b within a constant factor of optimal. So for every bit width, for every dimension, without needing to look at the data first. So there are two applications that this was tested on. One was KV cache quantization, and the second was nearest neighbor search. So in KV cache quantization application, this compresses the KV key and value vectors in a transformer's attention mechanism. This is critical for serving LLM with long context. And for the nearest neighbor search, it compresses a database of vector so that similarity search uses less memory and runs faster while keeping recall high. So now let's first understand the problem formally, what we are trying to do here. So we want a quantization map that compresses a d-dimensional floating point vector into b bits. If we set capital B equals to small b into d, then b is the bit width. Small b is the bit width. The average number of bits used per coordinate. So we also need a dequantization map that approximately reconstruct the original vector from the bits. We measure quality with two distortion metrics here. First one is MSE distortion, that is how close is the reconstructed vector to the original vector. And the second one is inner product distortion. If we compute the inner product between y and the reconstructed x, how far is it from the true inner product, that is y comma x. And for inner product quantization, we additionally require unbiasedness. On average, the estimated inner product equals to the true inner product. No systematic bias is in either direction. Why do we care separately about MSE and inner product distortion? Because an MSE-optimal quantizer is not necessarily a good inner product estimator. It can be biased. The paper proves this explicitly and proposes a two-state solution. Sorry, we will get there in the upcoming sections or chapters. So now let's move on to the coding part by initially setting up our Python file. Sorry. So for that we will first import the torch and then we will have import the functional library, that is torch.nn.functional as f, and then we will import numpy as np, and then we will import math library, and we will have from typing import tuple, optional, and list. These three we will be importing. So tuple, optional, and sorry, misspelled, optional and list, and from SciPy we will have optimizer. Sorry, we will from the optimize we have minimum scalar, and from SciPy.stats we will have norm, and we will import matplot, libpyplot. And finally, before we move on, we also have to set the manual seed to random 42, so that whenever we initialize random variables, it will always initialize the same, the value will be same for that. And same goes for the np as well, that is the numpy. And we will give the d equals to vector dimension as a constant 128, and b bits, that is target bit width, equals to 4, and number of vectors for testing will be equals to 10,000 for now, as we are doing it on a machine, so we have a limitation. Okay, so next we have to understand like what's the best we can do like in terms of theoretical lower bounds. So before we build the TurboQuant, let's understand the fundamental limit it's trying to approach. That is what makes the paper theoretically rigorous. The paper uses Shannon's source coding theory to prove a lower bound on distortion, a quantity that no quantizer, no matter how clever, can beat. The argument uses the Shannon lower bound. So Shannon proved in 1948 that minimum achievable distortion for compressing a source with entropy h of x using b bits is at least d of b greater than d divided by 2 pi e multiplied by 2 to the power of 2 divided by d with the product of h of x minus b. So for vectors uniformly distributed on the unit hypersphere, which is what we get after L2 normalizing our vectors, the entropy is h of x equals to log base 2 of surface area of the sphere. Plunging in and simplifying, so d of MSE of q is will be greater than equal to 1 divided by 4 to the power of b for any quantizer q with the bit width b, and d underscore prod of q is greater than equal to absolute of y square divided by d multiplied by 1 divided by 4 to the power of b. This is the absolute floor. No algorithm can achieve better distortion than 1 divided by 4 to the power of b for MSE. Let's build the intuition why this scaling makes sense. Every time you add 1 bit per coordinate, doubling the precision, the distortion drops by a factor of 4. That's a bit improvement in precision per coordinate, 4 times improvement in distortion. This is the fundamental rate distortion trade-off. So let's first set up the formula of function methods for this like lower bounds. So initially we define the def as theoretical lower bound and prod. This will take b float comma d int comma y norm, and this will be a float, yes, float with the default value as 1.0, and this will return float. And this will have a return value of y norm sq divided by d divided by that 4 to the power of b, that is the bit width. And next we will have next we will define a function or method that is theoretical lower bound for MSE. The lower bound MSE, this will have just one input, b float, and will be returning a float value again, and this will return the simple 1 divided by 4 to the power of b. I misspelled return, that's why it was complaining. Oh, okay, yeah, I corrected it. Then next we will have the TurboQuant MSE upper bound. This will take again just the b float, and this will return the float value as well, and the return statement will look like let's define a variable first, like constant, so that the statement is not very long. Constant math dot sqrt 3 and square root of 3 times math dot pi divided by 2, and this will have this constant. So this is roughly, the constant is roughly around 2.72. That's what we are trying to achieve, or that's what TurboQuant promises. So constant divided by, again, 4.4 to the power of b. And okay, yeah, so that's the constant factor regardless of dimension or bit width. No existing method achieves this. Next, let's move on to. Okay, now let's understand the core idea behind TurboQuant. It's elegant and the intuition is worth spending the time on. The problem with direct quantizing an arbitrary vector is that we don't know anything about its coordinate distribution. The coordinates might all be clustered near 0, or all near plus or minus 1, or have some weird bimodal distribution. An optimal scalar quantizer for one distribution would be terrible for another. And since we want a data oblivious algorithm that works without seeing the data first, we can't design a custom quantizer for each input. So the TurboQuant solution is we randomly rotate input vector first. Here's why it's brilliant. If you take any unit norm vector x and in r to the power of d and multiply it with a randomly orthogonal matrix R, the result Rx is a uniformly random point on the unit hypersphere. And a uniformly random point on the unit hypersphere has a very nice property. That is, each coordinate follow a beta distribution. And in high dimension, this distribution converges to a Gaussian with mean 0 and variance 1 divided by d. Furthermore, this is the crucial technical insight, like distinct coordinates of a random unit vector becomes nearly independent in high dimensions. This is a deeper result than just being uncorrelated, as near independence means we can quantize each coordinate independently using a scalar quantizer designed for the beta distribution without worrying about interactions between the coordinates. This is the power of random rotation. It transforms a worst case input, as you can see in the in this diagram in front, and enabling optimal scalar input after the rotation. With the different value of d, you see a different the peak values here. So let's now write this class or functionality for this class. We will have this class called random random rotation, and this will inherit torch dot nn.module class, and first we will initialize this the init, or write the constructor for this, maybe self comma d, that is the dimension, which is int, and the seed, that is also int, and by default will be 42. And inside this we will first call the constructor on initialize method of the super class. So init, AI is already auto completing everything. Self, I think we can just press tab if AI is completing, and let's see, self.d, that is fine. Nope, this is not what we want. The second thing will be seed dot d pad equals to 2 into math seal, correct. This is correctly done. Let me just fix the index, indent. And the third thing will be gen equals to torch dot generator. So this is the random diagonal matrix. This randomizes which dimension gets flipped. Fixed seed, so quantizer and dequantizer use the same rotation. And we will that the seed we will give is getting from the constructor parameters. And finally d equals to torch torch dot random integer function, that is 0 comma 2 comma self dot d pad comma I think generator gen, yeah, and we will convert it to dot float and multiply it by 2 and then minus 1, and we will register it. Self dot register buffer t comma d. And the second method will be def equals to Hadamard transform this is self this will have self comma x, that is the torch tensor, and return the torch tensor. So this is the fast Walsh Hadamard transformation in order of d of log d. The Hadamard matrix matrix H satisfies H the matrix multiplication of H and H cross H transformed equals to d multiplied by I. So H divided by square root of d is orthogonal. So let's see. Yeah, we can keep it or remove it. Let's see if AI has generated the code correctly. N equals to x shape minus 1, correct. We can assert a self.dpad, like input dimension must match the padded dimension. Then h will be equals to 1 and and result we have to define equals to x dot clone indentation, okay, and like this loop, okay, everything is not right here, let me write it again. So loop will be while h is less than n and result is equals to result dot view star result dot shape of 1 comma 2 comma and star h, okay, yeah, this is correct. And left will be equals to result up to h dot, we have to clone it, let's clone it, and the right will be is equals to nope, the right side of it, okay, yeah, this is correct. And result of spread operator comma colon h equals to left plus right, this is correct, and this is also correct. And the final result will be equal to result dot view star of result dot shape comma 2 fine, and finally h will be star equal to 2, and we return result divided by math sqrt of n. Okay, so this was the Hadamard transformation algorithm. You can read that more about on internet, like what does it do. So now let's write the forward transformation. Forward method. That is the training. We apply the forward pass on any neural network. So this will have if self dot d is less than self dot d underscore pad, that is the padding one. Oh, misspelled self both times. Self, and the pad size will be equal to self dot d pad minus self dot d. Lot of typos, sorry for that. And x equals to f dot pad from the functional torch functional library. That will be x comma 0 comma pad size. And then we apply random sign flips, that is x equals to x into self dot d, and we then apply Hadamard transformation, and we finally return the x. Okay, and then we we have the inverse function, that is the inverse rotation function. This will have self and x torch, correct? This will return torch, and the rest of them we do not need this. So x will be equals to x Hadamard transform on x multiplied by self dot d pad divided by math dot square root of dimension of the padding. And we again apply the self dot Hadamard transform on x. Actually transform of h equals to h, so h with the -1 rotation or transform will be equals to h divided by d pad. So that's why we are inversing, like doing the this inverse again. And we then have this x equals to self dot basically inverse sign flip self x into self dot d, and we again unpad it if self dot d is less than self or d pad, we unpad it, and we finally return x. So let me walk you through the implementation carefully. We use a structured random rotation instead of a full random orthogonal matrix. A full random d cross d rotation would require order of d square, and order of d square multiply accumulates for d equals to 4096, like a typical LLM hidden dimension. That's 64 million parameter just for rotation. That is way too expensive. So the structured rotation, that is r equals to d cross h, where h is the Hadamard transform and d is the rotation plus minus a diagonal, achieves the same theoretical guarantees in order of d log d, like time. The Hadamard transform is its own inverse up to a scaling factor, which makes the dequantization just as fast as quantization. The register buffer here stores the random diagonal as a non-trainable buffer. It's not a model parameter, but needs to be saved as and be consistent between quantization and dequantization calls. The padding next to power of 2 is necessary because the Hadamard transform requires dimension that are power of 2. We pad with 0 and unpad after the inverse. So next we move on to the Lloyd-Max scalar quantizer. So after a random rotation, each coordinate follows a known distribution, approximately Gaussian with mean 0 and variance 1 divided by d in high dimensions. Now we can design the optimal scalar quantizer for this distribution. The optimal scalar quantizer for a continuous distribution with 2 to the power b levels is called Lloyd-Max quantizer. It finds the optimal partition of real line into 2 to the power b intervals and assigns each interval a representative value like centroid to minimize the expected square error. Lloyd-Max algorithm iterates between two steps. First is a partition step, like given centroids C1, C2, C3 up to CK, assign each real value to the nearest centroid. The partition boundary are the midpoints between adjacent centroids. And the second step is centroid update, like given the partition R1, R2 up to Rk, set each centroid to the conditional mean of the distribution within that range. These two steps alternate until a convergence, and the result is globally optimal scalar quantizer for a given distribution. So as you can see in the diagram in front of you, like we have 1-bit quantizer or 4 levels 2-bit quantizer and 8-bit quantizer, like the Lloyd-Max quantizer. So now let's implement this Lloyd-Max quantizer. So for that we will now write another function called def Lloyd Max quantizer. Let me spell it correctly. Yeah, Lloyd-Max quantizer. This will have a input of n levels as integer. That is the number of level a quantizer has to go, as we seen in the slides, like 2, 4 or 8. The distribution, that is by default a Gaussian distribution. And we will have number of iteration to perform, like those two steps. We have partition step and centroid update step. So we have to iterate through these. So for that we are giving iteration of by default 1,000 iteration, let's see, and number of points equals to 100,000. 100, 1, 2, 3. Yeah, okay. So this will return. Let me get it down so yeah you can see it properly. Okay, and this will my bad. Yeah, this will return a tuple with the torch tensor and torch tensor values. Okay, now let's write it. So first thing, if it will check if dist equals to Gaussian, then it will have samples equals to torch dot random. Correct, this is correctly done by AI. Else if the distribution is equals to beta distribution, then we have samples nope, not this one, torch dot from numpy, and this will have np dot random dot beta 0.5 comma 0.5 comma number of points, and it will be multiplied by star to -1. Yeah, and we convert it to float. Else, if some other string value is there, we are handling it through raising value error like unsupported distribution value. Use Gaussian or that will be elif. Okay, yeah, that's why the AI was complaining. Editor was complaining, sorry. Yeah, use unsupported distribution, use Gaussian or beta. And finally, we have samples equals comma underscore samples dot sort. We will sort these samples, and then we will initialize x min comma x centroid. We are initializing centroid uniformly in the range of sample. So x max will be sample x max equals to samples n points 100 divided by 100, and this will return the item of it, comma samples and this has to be negative. Okay, let me first copy this and remove this. Yeah, okay, yeah, this is x min and x max, and the centroids now will be torch dot line space x min x1. Yeah, this is correct. X min x max and n levels. And now for the iteration part, the algorithm part, like for iterations in range it and n underscore itr, we have old centroids and we clone the centroids. Then step 1 is assign each sample to nearest centroid. So this will be dist equals to samples dot unsqueeze minus centroid. Yeah, this is correct, and the absolute value of that. And assignments equals to dist and argmin with dimension 1. And step 2, that is updating centroids to conditional mean. We will have new centroids equals to torch 0, not 0, like 0 and n inputs, n levels. Yeah. And for k in range n levels, we have mask equals to assignments equals to k. Only then if mask dot sum is greater than 0, then the new centroid will be updated to sample mask k of the mean of that. And else we have new centroid k as the centroid, the original centroid k, like keep unchanged if empty. And centroids will be updated to new centroids. Now to stop the this algorithm, we have to check for convergence. So we have this check centroids minus old centroids absolute max is less than equal to 1 e to the power minus 8. So, and if this is the case, then we print converged after iteration, yeah, this one, and we then break the loop. Now we compute boundaries as midpoint between adjacent centroids. So boundaries will be equal to centroid slicing the centroid array Android list. No, vector. Yeah, this is vector. Yeah. This is divided by 2.0. We need the float values, and we return the centroids and the boundaries, or let's say boundaries and the centroids. I think we define the boundaries first. Okay, these are torch, so doesn't really matters, but okay. So let's walk through this carefully. I forgot the equal to. Yeah. So the samples equal to sample.sort. We sort the sample from the distribution. This makes the Lloyd-Max iteration cleaner to implement since assignments will be contiguous. Then the centroids equals to torch.linespace line. We initialize centroids uniformly spread across the range of distribution. Good initialization matters for Lloyd-Max, and uniform initialization works well for symmetric unimodel distribution like Gaussians. The assignment step, like assignment equal to dist equal dot argmin, assigns each sample to its nearest centroid. This defines the Voronoi partition. Each region is the set of points closer to that centroid than to any other. The centroid update sample mask dot mean. Where is it? Yeah, sorry. The centroid update samples mask.mean sets each centroid to the mean of all sample assigned to it, the conditional mean of the distribution in that region. For MSE, the optimal representative for region is the mean, not the midpoint or anything else. The key insight by running this algorithm once and pre-computing the codebook, we avoid any per vector computation for codebook design. The codebook only depends on the distribution, which is known after rotation. So now let's quickly write the final method that is final function, that is compute MSE distortion before we move forward. So this will have be int number of samples. Number of samples will be int again, and by default 100,000. Oh, more than, sorry. 100, one extra zero. Okay, yeah, and this will return a float. Yeah. So the codebook I was talking about, basically this is the empirically this function empirically measures the MSE distortion of the Lloyd-Max codebook at bit width b. So codebook equals to code books of b and boundaries equals to code book boundaries, and I think centroids will be codebook centroids. Yeah, we initialize by that. Then we sample for standard Gaussians equals to x equals to torch dot random number n samples, and we quantize like assign to nearest centroid using boundaries, and boundaries partition the real line to into n levels. So assignments will be equal to torch dot bucketize x comma boundaries, and x quantized value, let's say quant equal to centroids of the assignments. And finally the MSE distortion will be equal to x minus x quant multiplied power of 2 dot mean and item, and we return the MSE. yeah, we save it. So yeah, this was the Lloyd-Max quantizer we wrote. Next, we will move on to understanding the MSE-optimal quant, like putting it all together. So now we have all the pieces for the MSE-optimal TurboQuant. The full algorithm is the quantization, that is L to normalize the input vector, apply random rotation, quantize each coordinate independently using the pre-computed Lloyd-Max codebook, store the integer indices. And the dequantization, look up each coordinates centroid from the codebook, apply inverse rotation, multiply by the stored norms. That's it. That's the entire MSE quantizer in 5 steps. So let's write the code for that. Class, we will define a class called turbo quant MSE. This will inherit torch dot nn dot module, and first we will initialize or write the init function method, self comma d, that is int b and seed 42. This will call the super int. This will call the initialization init method of the superclass, and it will assert b in code books, and we will return please generate one if code book for b is not found. Then we will initialize self.b with d, self.b with b, and self.random rotation with random rotation with d and a seed. Let's call it rotation only, not random rotation. And finally, the we will in the before like setting the boundaries, we will first load pre-computed codebook equals to codebook of b, and we will then like register buffer boundaries and centroids, self dot centroids. Okay, and next will be self dot number of levels, levels equals to 2 star b. And finally we can get rid of this self dot scale equals to math sqrt 3 sqrt not 3 sqrt math dot sqrt, yeah, sqrt of self dot rotation of dpad dot d padding. That's it. Then we will define the method quantize. This will have self comma x, that is the dots. This will have the input self comma x torch tensor, will return the torch dot tensor, and let me remove this. AI is not generating it correctly. We have norms equals to x dot normalize dim equals to -1 comma keep dim equals to true, x unit equals to x divided by norm plus 1 e minus 9. step 2, so this is the L2 norm, normalize and save norm. Then we will, step 2 will be random rotation. So x rot or rotation equals to self dot rotation x unit. This is correct. Then step 3 is scale to match the code book. We scale to match the scale of that. So x scaled will be equals to x rot multiplied by self dot scale. And step 4 is basically per coordinate scalar quantization using codebook. Like assigns each value to the interval defined by the boundaries. So indices equals to torch dot bucketize x scaled comma self dot boundaries, and we finally return norms dot squeeze -1 and comma indices. And for now, finally, last function of this class is dequantize. Sorry, not the last one, second last. Dequantize self dot it will have norm test torch tensors indices and returns the torch tensor, and it will have x approx scaled equals to self dot centroids indices and x approximately undo scaling, we divide by the scale. Then approx inverse rotation, so x approx unit, we invoke self dot rotation dot inverse that we defined earlier, and it has, we will slice that as well. Yeah, this is correct. And finally rescale by stored norms. So x approx will be x approx unit multiplied by norms by unsqueezing -1, and we finally return x approx. And now the final one is the forward pass. This will have again self x torch tensor, and it will return not tuple, just the single torch tensor. And this will have normal initialize norms and indices with self dot quantize, and return self dot dequantize by norm and indices. So let's walk through the key design decisions here. So norm equals to x dot norm, we store the L2 normalization separately in float 32. This is mentioned in the paper. The unit norm assumption is W log. For vectors that aren't unit norm, we normalize first and store the norm. Since norms are just scalar values, storing them in float 32 adds 32 bits total per vector, negligible compared to the b cross d bits for the quantized coordinates. Then x scaled equals to x rot multiplied by self dot scale. So after a rotation, each coordinate has variance of 1 divided by d pad. Since the rotated unit vector's coordinate shares the total norm squared of 1. Our Lloyd-Max codebook was designed for n 0,1, so we scaled by square root of d underscore pad to bring the variance to 1 before quantizing. And the torch bucketize method, this is the PyTorch built-in efficient lookup that gives that given sorted boundaries finds which interval each value falls into. For n levels equals to 16, like 4-bit, this partitions each coordinate into one of 16 buckets. And finally, the self-centroid indices, this is the simple integer indexing. Why I'm not able to find it self. Yeah, this one. Each index maps directly to the pre-computed centroid value. This is the entire dequantization per coordinate, like one lookup. Okay, now let's move on to the next section. Here is the thing. You might think, great, we have a MSE or optimal quantizer done, but there is a subtle problem here. In KV cache application and in nearest neighbor search, we don't care about reconstructing a vector with low MSE. We what we care about is inner product, and attention scores are computed as q dot product of q and k transpose, and nearest neighbor search computes a query the dot product of query and database vector for every database vector. We need these inner product to be accurate, not the reconstructed vectors themselves. And the paper proves something counterintuitive. That is, MSE-optimal quantizers are biased for inner product estimations. Here is the intuition. When we quantize a coordinate xi, we round it to the nearest centroid ck. The rounding error, that is ei equals to ck minus xi, is not on average. It depends on where xi falls relative to the boundaries. The mean of the rounding error within each interval is 0 by centroid update rule. But the correlation between the error ei and the query coordinate yi can be non-zero. Concretely, consider a 1-bit quantizer with the centroid at negative alpha and positive alpha. If x of I is greater than 0, we map it to positive alpha, but the true value might be anywhere between 0 to 1. The inner product estimate yi into alpha can be systematically off from yi into xi, depending on the distribution. So as you can see in the diagram as well, the MSE TurboQuant has some biasness, but inner product needs some unbiasedness into it. So the unexpected inner product from MSE quantizer systematically overestimate or underestimate the true inner product. This is a fatal flaw for attention mechanism. Biased attention score lead to wrong probability distribution. So to solve this, the bias problem, TurboQuant introduced two stage approach. But first we need to understand the building block, that is QJL, or quantized John Lindenstrass transform. QJL is an extremely elegant 1-bit quantizer for inner products. Here is how it works. You given a vector x, multiply it by a random Gaussian matrix S, and take the sign of each entry q underscore qjl of x equals to sign of x s dot x, where s maps to r to the power of d cross d, and has IID of n comma 0 comma 1 entries. Then you dequantize, given the sign s equals to sign of s of x, the estimate of x is q underscore qjl and to the power of minus 1 comma z, that is equals to square root of pi by 2 divided by d into s transpose multiplied by z. Why this works? The key relationship between the sign of a Gaussian product and the angle between vectors. If s of I is a random vector, Gaussian vector, then E of sine of s of I into x multiplied by s of I in dot y will be equal to square root of 2 divided by pi multiplied by x comma y. This means square root of pi by 2 divided by sine of s of I dot x into s of I dot y is an unbiased estimator of x comma y for each row I. Averaging all over D, rho gives the QGL inner product estimate, and since each estimate is independent, the variance decreases as 1 divided by D. So now let's implement this QJL class. So for this we will first call the class QJL, and it will have torch dot nn dot module as like its parent class, or we will this class is inheriting the module class, and the first method is again def init method. This will again have the self, and we have int comma we have the seed again, and this time the seed we can keep it as 1 2 3. So we again initialize the superclass, then we assign a self.d to with the parameter, and then we have the scale, the self.scaling. This will be equal to math.sqrt and math.py divided by 2 and divided by d. And then again we have this the fixed random Gaussian matrix, gen equals to torch generator, and gen manual seed will be equal to gen dot manual seed, and we will register it. Before that we have to make call that let's store that matrix in a variable torch dot random number d comma generator equals to gen, my misspelled torch, and now we register self dot register buffer with s comma s. And the first method that we will use is again quantize. This will have self and x as torch tensor as its parameter, and will return the torch tensor. And this first we will have the project through random matrix, like projected equals to x at self, this is the matrix multiplication, self dot s dot transpose. Let's give it some space and yeah. And next let me remove this everything. And next we will have like take sign, z equals to torch dot sign projected, and finally we have z equals to torch dot where z equal to 0, torch dot 1 like z comma z, and finally we return the z. Okay, so the next one will be dequantize. Again it will have z as torch tensor and self. So for that now the first line will be x approx. We are basically reconstructing approximate vector from signs. So x approx prox equals to self dot scaling and yeah, but this has to be scaled, not just z, the dot product, sorry, matrix multiplication, and we return x approx, and finally we define the inner product estimate. This will again have self z and y, the quantized x and query vector. So self comma, let me do it like this. Oh, okay, and z is torch dot tensor, and y is torch dot tensor again, and this will output torch dot tensor, and it will first directly estimate inner product y comma x from quantized z, more efficient than dequanting x and then dotting with y. So this will be sy equal to y at the rate self the transpose of s, and if sy dot dimension is equal to 1, then we do sy equals to unsqueeze 0 and to match the dimension, and we return self dot scaling z star multiplied by sy and sum of dimension minus, and we sum it through with the dimension equals to -1. And finally the forward method, again it will have the self comma x, that is torch dot tensor, and it will simply return self dot dequantize of the quantization. Quantize, yeah, okay. So let me walk this through. So the projected did I miss something? Oh, I buffer, yeah, okay, and dequantize, fine. Yeah, so as I was saying that this projected equals to x, this multiplies the batch of input vector by like transpose of s. Each row s of i of s computes the dot product s of i dot x for each input vector. The result is a batch comma d matrix of projections, and then the s equals to torch dot signed projected takes the element wise sign. Each coordinate becomes either +1 a positive projection or -1 negative projection. This is our 1-bit quantization. We only store whether the projection was positive or negative. Then the x approx equals to self scaling line, the dequantization part. We multiply the signs back through s. Note s not transpose of s here. This computes transpose of s is z, because z matrix multiplication of z and s will be equal to matrix multiplication of s transpose and z transpose, and again taking the transpose of that. The scaling factor square root pi by 2 divided by d corrects the expected magnitude. The inner product estimate is the practical method for KV cache and near neighbor application that was implemented or used by the paper. So instead of fully reconstructing x and then dotting with y, we directly estimate y comma x from the quantized bits. This is more efficient. We pre-compute sy, the query projected through s once, then take a dot product with the stored signs. Okay, now we have both pieces. So let's build the inner product optimal TurboQuant. The problem, like MSE are biased from inner product. QGL is unbiased at 1 bit, has high variance. The solution, combine them in 2 stages. Stage 1, apply the MSE quantizer at b minus 1 bits. This minimizes the L2 norm of the residual, and stage 2 is apply QGL to the residual R. The residual has a small L2 norm thanks to stage 1. So the QJL estimate of inner products with the residual has small variance. The final estimate of y comma x is y comma q MSE with the power like raised to the power of -1 q MSE of x plus QJL estimate. The first term has bias but low variance. The second term remove the bias, QGL is unbiased, while adding controlled variance that's small because mod of R is small. Together, unbiased and low variance at B bits total. So now let's write the complete class of TurboQuant inner product, the solution of this paper. So to do that, we will define a class called let's say TurboQuant inner product maybe, and this will have torch again torch.nn.module as input as a superclass, and define again the init function or init method first. This will have self comma d comma b and seed. So instead of the seed, let's call it MSE seed. This will be int42, and we have another QJL seed that is int32. Int with value 1, 2, 3. And we let's see if the AI has written the right code. So we call the super init method of the superclass, and we then assert if b is greater than equal to 2. We need at least 2 bits total, like 1 for MSE stage plus 1 for QGL. So this will be let's say need at least 2 bits total, 1 for MSE stage and 1 for QGL stage. Then we initialize self.d, self.b, and not rotation. Let me remove the remaining. This one. Let me remove everything else as well. We will write it. So self.b. Then we the stage 1 is self dot. We define the stage 1 self dot MSE quant. Let's say, and it will be TurboQuant MSE with d b minus 1 and MSE seed, and the stage 2 is self dot QJL, of course, and this will be equal to QJL d, and seed will be equals to QJL seed. Now we define the def quantize method. Quantize. So self, this is correct. It will return the tuple. This will be the 2-stage quantization. So let's write it. Norms. Stage 1 is MSE quantize. So norms, comma MSE index this time idx equals to self dot MSE underscore quant dot quantize x, and then we have compute MSE reconstruction to get the residual. So x equals to MSE recon equals to self dot MSE quant dot dequantize, and it will pass norms and MSE index. Now the residual is equals to I guessed it correct, x minus x MSE con. Then comes the stage 2, that is Q, the unbiased quanti. I'm forgetting it. QGL on residual. Sorry. So QGL bits equals to self dot QGL dot quantize, and we residual, and finally we return norms, comma MSE index and QGL bits, and then we have the estimate inner product function. So this will be self comma norm, that is torch tensor, then MSE index and a QGL bits, and finally y, and this will output the torch tensor. Estimate from quantized representation without fully dequantizing. This is the efficient path for attention and nearest neighbor search. So in that, let's see if I wrote it correctly. X MSE recon equals to self dot MSE quant dequantize norm and MSE correct. Then residual estimate, or we can wait. Before that, we have IP, that in a product MSE equals to x MSE recon slash y, and we have to unsqueeze it dot unsqueeze sorry, and we then the stage 2 will be IP. This autocomplete is wrong. IP QJL equals to self dot QJL dot inner product estimate with QJL bits and y, and now we finally return the IP MSE and IP QJL. So the two stages that we just discussed. Now for the def dequantize method, we have correct self, norms, that is torch tensor, MSE index and QJL bits, and it will return torch.tensor. So it will have the MSE reconstruction, x MSE reconstruction, that is self.MSE quant, and it passes the norms and MSE index. We have residual reconstruction, that is self.QGL dequantize with QGL bits, and we return the x MSE reconstruction plus the residual reconstruction. And finally, we have the forward method. This will have self and x torch tensor, not y, self comma x tensor torch dot tensor, torch dot tensor, and torch tensor will be returned. So it will first call the self dot quantize, that will be that will return norms, MSE IDX and QGL bits, and it will then return the dequantized call the dequantized method with these parameters. So the residual equal to x minus where is that Yeah, here. X minus X MSE recon, the key line. The MSE stage already reconstructed a good approximation. The residual captures what was lost in quantization. By construction, this residual has small L2 norm. That's exactly what the MSE stage minimized. The self QJL quantize, sorry, where is that? Yeah, this one. The self QJL quantized with the residual. We apply the 1-bit QJL to this small residual vector, because the approximation or the absolute value of residual is small. The MSE stage did its job. The inner product with any query y is also small. The QJL variance bound applies to the full vector, but here we are applying it to the much smaller residual, dramatically reducing the effective variance. Then the IP MSE and IP QJL, the two contribution sum to an unbiased estimate. The MSE term provides low variance but potentially biased estimates. The QGL estimate terms corrects the bias. Together they achieve both unbiased and low variance. So the this video is already pretty long, so we will not be discussing any let's say the implementation of both the application that were introduced in the paper, like application 1, the KV cache quantization. In a standard transformer, the KV cache stores key value vectors for all pass tokens. For a long context of L tokens, this is 2 times L times D floating point vectors. At 32-bit 100K context with dimension 128 takes 3.2 GB per layer, with 32 layers over 100 GB for one request. With TurboQuant at 4-bit 8 times compression, that drops to around 13 GB with 3.5 bits. We are near 11 GB. And the paper shows that at 3.5 bits, the equality loss is essentially 0. The key insight for KV cache, we need one-line quantization. Tokens arrive at it one at a time. We can't wait to see the whole sequence before building a quantization codebook. TurboQuant is perfectly suited. It's data oblivious, so it applies instantly to each new key or value vectors as it arrives. And you can see in the diagram the different quantization that TurboQuant works on, that gives the different size comparisons. So for the nearest neighbor search, the second application that the paper discussed, we finding the most similar vector in a large database for a given query. This powers semantic search, recommendation system, and RAG, that is retrieval augmented generation. In the method product quantization is the standard approach in nearest neighbor search libraries like FAISS. PQ or product quantization splits the vector into subvectors and quantizes each subvector independently using a k-means cookbook. But PQ has a major drawback. It requires expensive offline pre-computing or pre-processing to compute the codebook from the data. So TurboQuant eliminates pre-processing entirely. Since it's data oblivious, the codebook is fixed based on the distribution after rotation, not the data. So indexing time is essentially 0, and new vectors can be added to the database instantly. So these were the two application that TurboQuant paper worked on or took as example. So how to implement that, I will add the code later in the final file. because we are already this video is already very long. If I code it from scratch, it will be much longer. So the what paper actually achieved the let's look on that before we wrap up. So I want to show you the actual numbers from the paper and the Google research blog, because they are striking and they make everything we build today feel very real. First one, as we discussed, KV cache on long bench. The paper tested TurboQuant on Llama 3.v 8-bit instruct across long bench. A comprehensive benchmark covering question answering, code generation and summarization with long context. At 3 bits per coordinate, which is 10.7 times approx compression over float 32, TurboQuant maintained essentially the same score as the uncompressed baseline. No training, no fine tuning, just compression applied to the running model's KV cache. The comparison baseline was Kiwi, the previous state-of-the-art KV cache quantizer. TurboQuant essentially matched or beat it across all task types, despite being simpler to implement and having stronger theoretical guarantees. When you have a provably near optimal algorithm, it doesn't just win on benchmarks, it win like reliably. Because it's not a cherry picked to fit any particular data set. The second benchmark or the number I want to discuss is the needle in the haystack. This is the stress test for KV cache compression. You hide one specific fact inside a document of, let's say, 128,000 tokens and ask the model to retrieve it. If KV cache compression loses even a handful of important tokens, the model fails to find the needle. TurboQuant achieved perfect scores on this benchmark at 3.5 bits. This was a 6 times memory reduction with zero degradation. The Polar Quant stage 1 on its own also performed nearly lossless on this task, showing that even without the QJL residual correction, the rotation plus Lloyd-Max codebook alone is already very strong. The third point is the speed, that is 8 times on Hopper 100 or H100. So here is the result that makes this practically transformative. On H100 GPUs, 4-bit TurboQuant achieved an 8x speed up over unquantized float 32 keys when computing attention logits. This was measured against a highly optimized JAX baseline, not a slow naive implementation. The speed up comes from two places. First, integer arithmetic is faster than floating point. And second, and more importantly, smaller data means more of it fits in the GPU's fast on-chip cache, and memory bandwidth is used more efficiently. When you are bottlenecked by moving data between GPU, DRAM and compute units, which is exactly what happens during attention, as we discussed in our LLM inference series, cutting your data size by 8 times cuts your bandwidth requirement by 8 times and gives you proportional speed up. The fourth thing was vector search on Glove versus PQ and RabbitQ. For nearest neighbor search, the paper evaluated on the Glove dataset with dimension equals to 200 word vectors against PQ, that is product quantization, and RabbitQ. Both of these baseline use expensive offline k-means training on the actual dataset to build their code books. They see the data first and tune it later. TurboQuant, with zero pre-processing and completely data oblivious codebook, achieved superior recall ratio at every bit width tested. It beats methods that had the advantage of seeing the data. This is the point the paper is making. Like, the theoretical optimality of approach overcomes the advantage of data-specific tuning. This is running in production at Google. So Google research blog explicitly mentions that TurboQuant is being used for Gemini KV cache. This is not a research demo or a paper experiment. It is like running right now on one of the largest language model in the world, compressing the KV cache of real users at Google scale. What we coded today, the random rotation, the Lloyd-Max codebook, the QJL residual correction, is the algorithm doing that work in simplified form. So what we built versus the full implementation, like a few engineering gaps worth knowing about, like the Hadamard based rotation we implemented is the standard efficient approach. The paper specifies random orthogonal matrices, but in practice, like D multiplied by H, the diagonal times Hadamard has the same theoretical properties and runs in order of D log D rather than D square. The Lloyd-Max codebooks we computed numerically matches the paper's pre-computed codebooks. In a production system, you would ship these pre-computed rather than running Lloyd-Max at startup. The 8 times GPU speedup requires custom CUDA kernels, packing quantized indices into int4 format and using tensor cores for the integer matrix multiplication. Our PyTorch implementation is pedagogically correct but not production optimized for speed because we are of the hardware limitations. The path to replicating the speed up benchmark is like clear engineering work, not new algorithm. Paper also discusses like entropy coding of the codebook indices. Since coordinates after rotation follow a beta distribution, some indices are more probable than others. And Huffman coding can squeeze out additional bits beyond the nominal bit width. We skipped this, but it's a clean extension if you want to push compression further. So to give you a recap of what we built today, so we have or how our TurboQuant works. You have a high dimension input scattered vectors. You apply a random rotation, that is the beta distribution. Then you scale the quantization, which gives you the residual, and then you apply the 1-bit QJL quantization that on the residual that makes it unbiased, and then you dequantize it to get the appropriate output. This paper is like beautiful example of theory meeting practice. The lower bound aren't just interesting math; they tell us how close we get, which drives the design. And the random rotation tricks that unlocks optimal performance is simple enough to fit in a few line of code. So I will link in the below. I will drop down the link to the in the description below. I will drop down the full code and also the paper, the TurboQuant paper, and the QJL and a polar quant paper as well, from where this ideas were taken or these ideas were merged. And if you like this video, hit subscribe. Thanks for watching. See you next time.